This is an example problem of how to use the universal law of gravity in cases where you've got more than two particles or more than one particle exerting a force on another one. Okay, now, we've already seen in previous lessons that Newton's universal law of gravitation is that the force that two objects exert on one another due to gravity is given by the gravitational constant big G times the mass of the two particles multiplied by each other over the distance between the two particles squared. Okay. But what if there's more than two particles? What if, for example, I have the moon here, and the Earth here, and the sun way over here? What if I wanted to find the force on the moon due to both the Earth and the sun's gravity? Well, what I would do is I would find the force on the moon due to the Earth and the force on the moon due to the sun, and then you would add those two forces together as vectors. In other words, let's call the moon object 1, the Earth object 2, and the sun object 3. And the goal is to find the total force on the moon due to the Earth and the sun. Well, that would be, first I would find the force on object 1 due to object 2. That would be G times M1, M2 over the distance between object 1 and object 2 squared. Then I would find the force on the moon due to the sun, object 3, which would be equal to big G times M1, M3 over R1, 3 squared. Once you've found those two forces, then the total force, excuse me, let me erase this, then the total force on the moon is equal to the vector sum of F1, 2, and F1, 3. Okay, and this method works for any three objects. If you want to find the force on one of them due to the other, then you would find the first force, then the second force, add the two as vectors, and that gives you the total force. It doesn't have to be for the moon, it doesn't even have to be for objects in space. The same technique would work for billiard balls or any other things that are exerting gravitational forces on one another. All right, so first, let's find F12, the force of gravity on the moon due to the Earth. Okay, well, let's say then F12 is equal to big G, that's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Okay, times, now I need the mass of the Earth, which we'll have to look up. Okay, the mass of the Earth is 5.98 times 10 to the 24 kilograms. And we need the mass of the moon, which we will look up. Okay, mass of moon, 7.36 times 10 to the 22 kilograms. Okay, and then we need the distance between the Earth and the moon. Okay, which is around 4 times 10 to the 6 kilometers, or 4 times 10 to the 9 meters. Okay, and we'll square that. Excuse me, that should be 10 to the 8, because it's about 4 times 10 to the 5 kilometers, so it's going to be 4 times 10 to the 8 meters, not 4 times 10 to the 9 meters. And that will be squared. Okay, now you can multiply all that together on your calculator. And again, I recommend you follow along with this on your own calculator, just mostly to make sure you know how to use your calculator, because I have a lot of students who make calculator errors. So we have 7.36 times 10 to the 22 times 5.98 times 10 to the 24 gives me 4.4 times 10 to the 47. Multiply that by 6.67 times 10 to the minus 11, giving us 2.94 times 10 to the 37. Then we divide by 4 times 10 to the 8 squared, which gives us 1.83 times 10 to the 20. 1.83 times 10 to the 20. All right, we have kilograms and kilograms here, canceling kilograms squared there. Meters squared here, canceling meters squared here. We're left with newtons. Okay, and the way I've drawn the picture, so this just tells us the magnitude of the force. The direction is attractive. So since the moon is object 1 and the earth is object 2, the earth attracts the moon, so that force is this way in the picture, okay, which would be down in my picture, at least. If we were kind of looking at the solar system from above, then it would be that way. All right, now we need to find F13. That will be same gravitational constant, okay, times this time the mass of the moon, which is still 7.36 times 10 to the 22. We need the mass of the sun, which we will look up. The mass of the sun is 1.99 times 10 to the 30. Okay, so that's times 1.99 times 10 to the 30 kilograms. Divide that by the distance between the moon and the sun. Okay, which is approximately 1.5 times 10 to the 11 meters. 1.5 times 10 to the 11 meters, and that will be squared. Okay, now we need to multiply all of that together. 6.67 times 10 to the minus 11 times 7.36 times 10 to the 22. This is 4.9 times 10 to the 12 times 1.99 times 10 to the 30. This is 9.77 times 10 to the 42. Then we divide that by 1.5 times 10 to the 11. Squared. It's 4.34 times 10 to the 20. 4.34 times 10 to the 20 newtons. Okay, now again, this is attractive. The sun attracts the moon, so that force would be that way, to the right in my picture. Okay, now I need to add these two forces as vectors. So you can't simply take 1.83 and add it to 4.34 and be done with it, because that would be adding them as scalars. You could only do that if they were pointing in the same direction, and they are not. So instead, we must add them as vectors. What you need to do is find the x and y components of each of those forces and add them as vectors. So if we make our coordinate system like this, centered at the moon, then you can see that the Earth-Moon force has only a y component, okay, and in fact it would be in the minus y direction, and that the Sun-Moon force has only an x component, and that it would be in the positive x direction. So I don't have to add these components, since the total x component, okay, you would have the total x component is equal to F12x plus F13x but F12x is 0. So the total x component is just 4.34 times 10 to the 20 newtons. Okay, for the y component, that would be F12y plus F13y. F12y would be negative 1.83 times 10 to the 20 plus 0. Okay, I'm going to erase the bottom half of the screen now, because I've already written the things that we need up there, and I'm running out of room. Okay, so the magnitude of the total force we then get by using the Pythagorean theorem. The square root of the total x component squared plus the total y component squared. This is good review for the final exam, by the way, because you'll be needing to add vectors by components when the final comes, and it's been a while since we've added vectors by components, so this is good review. Go back and look at chapter 4 if you don't remember how to do this. Okay, so that's equal to the square root of the 4.34 squared, the 1.83 squared, all times 10 to the 20, 74.34 times 10 to the 20 squared plus 1.83 times 10 to the 20 squared. So that's 22.18 times 10 to the 20. I'll take the square root of that, getting us 4.7. 10 to the 20 newtons. That is the magnitude of the total gravitational force on the moon due to the Earth and the Sun, if the moon were in the position that I've drawn it here. Okay, now, by the way, when you're using the Pythagorean theorem here, don't get thrown off by that negative sign. Remember, when you square a negative number, it becomes positive. Now, this tells us only the magnitude of the force. It doesn't give us the direction. To find the direction, we'll need to draw the triangle. Okay, so we have an x component of approximately 4 this way, and then a y component of about 2, roughly, down this way. Okay, this would be 4.34 times 10 to the 20, and this is 1.83 times 10 to the 20. So the direction will be off that way. If we want to find the angle, then we can use tangent. Theta is going to be equal to the inverse tangent of opposite over adjacent. Opposite, in this case, is 1.83, and adjacent is 4.34. The 10 to the 20s would cancel there, so you don't have to type them in unless you just want to. So we have 1.83 divided by 4.34, giving us 0.422. And then we use the inverse tangent function. That is 22.9 degrees. 22.9 degrees below the horizontal would be the direction. And that's the end of the example. So, as I said, this will work for any combination of 3 masses. There will be times when you won't necessarily have a 0 for one of your components. That made the math a little easier in this example. But the basic method that I showed you here will work for any 3 masses. If you have 4 masses, then you would simply say, well, the total force is just the vector sum of F12 plus F13 plus F14. You could just keep going. No matter how many masses you have, you just keep adding terms. One other comment. This method of finding the net force on a mass due to 2 other masses is very similar to finding the net force on a charge due to 2 other charges, which you will be doing in Physics 202. So if you're going to take Physics 202, keep this in the back of your mind. You'll be using exactly the same technique when you start dealing with forces on positive and negative charges.